In this set of class notes, we're going to expand on what we learned about polar coordinates in the video notes. And we're going to focus on graphing equations that are written in polar coordinates. And then we're also going to, and this is what we're going to start with, is converting in polar coordinates points, but ones that don't give you special values for angles. So in the video notes, every time that we uh, turn rectangular coordinates into polar coordinates, the angle always turned out to be a special value. Okay, so what do we do if that's not the case? All right, so one of the things you remember is that we did always express our angle in radians, right? So things like pi over 3, 3 pi over 4. So we want to continue to express things in radians, right? So make sure that your calculator is in radian mode as you're doing these. All right, so these are three problems here that I would really encourage you to try yourself first. So examples 1, 2, and 3. Try them yourself. And then look critically at your answer. Make sure that the angle and the R value that you get when you're converting these points into polar coordinates, in fact, agrees with where you know the point has to be. All right, so let's look at example 1 here. Hopefully, given this one a try. And first thing I think to note here is that we can quickly just ballpark whereabouts 2, -3 is. So here's 2, -3. So we know we're talking about a point right there. All right, so what do we know? We know that r squared, right, is going to equal x squared plus y squared, right? We know that. So r squared is equal to 2 squared plus -3 squared, which is equal to 13. So r must equal the square root of 13. And the square root of 13, that's between the square root of 9 and the square root of 16. So it's somewhere between 3 and 4. And that seems reasonable, right? That this hypotenuse would be between 3 and 4. So I'm good so far. But what about the angle, right? So we know that the angle, the tangent of the angle, excuse me, should be y over x. So that means the tangent of theta is equal to -3 over 2. So remember, what we want to try to do here is say, okay, let's take the tan inverse of -3/2. And that gives you approximately -0.983. So we're saying theta is about -0.983. All right, well, does that make sense? Well, I am going, it looks like, in the negative direction here. So that's a good sign. And then the other thing that I would say is that we know that this would be -1.57, right? We should have memorized that pi over 2 is 1.57. So -1.57 would be down here. So I like my angle that I've got here. So I'm thinking that I'm really comfortable saying that theta is the tan inverse of this, which is about -0.983. And so to express this in polar coordinates, I would start with my r, right? And then give my theta. All right. Let's try another one. All right, I think again it's useful to start by just sketching it in rectangular coordinates, give our brains an idea of what we're looking for. So -4, 9. That's the point we're looking for. All right, so we'll start with our r. R squared should be -4 squared plus 9 squared. So r squared would be 16 plus 81. So that's going to give me 97. So r is equal to the square root of 97. Okay. Square root of 97 is almost 10. Does it make sense that this distance here would be around 10? I think so. If you have 4 and 9 as the legs of the triangle, I think that really does make a lot of sense. All right, how about the angle? So the tangent of our angle should be 9 over negative 4. Now, when I take the tan inverse of 9 over negative 4, it's going to spit out to me. What is it going to spit out to me? Oops, I forgot to write it down. I apologize. So it's going to spit out to me negative 1.15. Okay, now negative 1.15, thinking about what we did last time, negative 1.15 would be going in the negative direction, but we know negative 1.57 is down here, so negative 1.15 would be something like this. So that is not the direction we wanted to go to get to our value, right? That's negative 1.15. Okay, but if you look at this in relation to what we wanted, what is it? Well, it's 180 degrees away. So what I need us to remember is that, remember, tan inverse, we'll write this over here so we remember well, tan inverse only spits out values between negative pi over 2 and pi over 2. That's all the tan inverse ever spits out. So what can happen is the angle that it's giving you is actually pi, or 180 degrees away from the angle you want. So what we're going to do here is we're going to say that theta is not quite equal to tan inverse of negative 9/4. It's equal to that plus pi, and negative 1.15 plus pi, and that's going to give you about 1.99. So be careful. The tan inverse is not always going to automatically spit out what you want. You may need to adjust your angle. And so I would say that this is the square root of 97 and then 1.99. All right, one more example. So we've got the point negative 5, negative 4. So again, we'll sketch what that looks like. So negative 5, negative 4. That's the point we're searching for. So r squared is negative 5 squared plus negative 4 squared. We get 25 plus 16, so r squared is equal to 41. So r is the square root of 41. Square root of 41 is between the square root of 36, which is 6, and the square root of 49, which is 7. Does it seem reasonable that this distance here is between 6 and 7? I would think so. All right, so how about the angle? Now, right off the bat, learning the lesson from last time, I should know that when I punch this in the calculator, I am not going to get the true angle, because negative pi over 2 to pi over 2 is the right half here. And so my angle is definitely not in the right half. It's not in quadrant 4 or 1. And so I know ahead of time that it's going to give me the wrong angle. I actually know ahead of time it's going to give me this one right here, right? That's the angle it's going to give me. So I'm going to have to add pi once again. And as you can see, if we punch this in to our calculator, it's going to spit out 0.67, 0.675. So if we say theta, well, if we take tan inverse of negative 4/5, that's approximately 0.675. Okay, we need to understand that, well, 0.675 is definitely up here in quadrant 1, so we got to go pi more. So we say theta is that plus pi. So theta is approximately 3.82. And we know that 3.14 is here, right? So 3.82 certainly seems reasonable as the angle that I should get here. So we get r equals the square root of 41, and theta equals 3.82. All right, so the other business that we have here in this set of notes is we want to learn how to graph um, in polar coordinates. So let's think about when you first learned to graph, um, back in your first algebra class, when you first learned to graph a line, probably what your teacher had you do was make a table of x and y values, right? And you'd plug x's in, um, and so, you plug x's in. Let's say we had y equals 2x plus 1. You just plug different x's in, and that would tell you uh, what to do on the graph. So if I plugged in, a 0, I knew that y would equal 1. So that told me to go x equals 0, y equals 1, and put a dot. When x is equal to 2, y would equal 5. So then I would go over 2 and up 5, and I'd put a dot. And you would figure out by placing all these dots, based on this table you made, what the graph had to look like. So we're going to go back to those kinds of basics. But what we'll do is we'll think of r kind of like our y and our theta kind of like our x, because we plug in thetas to figure out what r should be. So we'll say theta on the left, and then over here r on the right. So let's keep this easy at first. If theta equals 0, we have 3 times the sine of 0, which is equal to, well, the sine of 0 is 0, right? So that means when theta is 0, r is 0. So that means you don't go out from the origin at all. So you're just going to put a point right there at the origin. How about pi over 6? So at pi over 6, we have 3 times the sine of pi over 6, which is 3 times a half, which is 1.5. So, and one of the things to remember here is that on these polar graphs, we talked about this before, but right, this is pi over 12. That's pi over 6, pi over 4, and then pi over 3, 5 pi over 12, and then pi over 2, right? So don't make the mistake of thinking this is pi over 6, right? Pi over 6 is 2 pi over 12. So when I go to pi over 6, I'm at 1.5. So this circle is a radius of 1. This is a radius of 2. So 1.5 is halfway between those two. And then if I go to pi over 4, 3 times the sine of pi over 4, that's 3 times the square root of 2 over 2, and that's about 2.12. So out here, 2.12 puts me right about there in this neighborhood. And pi over 3, 3 sine pi over 3, which is 3 times the square root of 3 over 2, which is about 2.60. So 2.60 puts me right about there. And then pi over 2 is 3 times 1, which is 3. So that means up here I'm at 3. All right, so at this point, what I want to do, though, is go a little faster through this. So you get the idea. I'm literally plugging them in, figuring out what I get, but ultimately I'm going to settle for an approximation if the number isn't nice. So if I do 2 pi over 3, I get 2.60. So again, here's 7 pi over 12. This is 2 pi over 3, 3 pi over 4, 5 pi over 6, 11 pi over 12, and then pi. So here I'm at 2.60 again. So that's actually the same as I had on the other side at pi over 3. And then at 3 pi over 4, I'm at 2.12. So that puts me right about there. At 5 pi over 6, I'm at 1.5, which puts me there. And then at pi, I'm back at 0 again, which puts me back there. Now, if I stop there, it's gonna, what does that form? Well, it kind of looks almost like it forms a circle. So I'm gonna do my best to kind of hook these up in a circle. Now, what we are going to do is we're going to talk about how to use technology to see if we were right about this, but it certainly looks like a circle. Okay, but what happens if I keep going? All right, well, do I get something down here? So let me just do this next part in red. What if I did 7 pi over 6? If I did 7 pi over 6, I'd get 3 times the sine of 7 pi over 6, which is 3 times negative 1/2, which is negative 1.5. So when I'm pointed over here at 7 pi over 6, I'm pointed this direction, it says negative 1.5. Well, if it was positive 1.5, that would put me right here. But negative 1.5, remember, means go 180 degrees in the opposite direction. So 180 degrees in the opposite direction puts me back here, right? 1.5 in the opposite direction, so it puts me there. If I was to do, uh, let's see, 5 pi over 4, guess what I would get? Negative 2.12. So what does that mean? I'm at 5 pi over 4. Instead of going 2.12 out this way, I go backwards 180 degrees the other direction, 2.12. And so what happens in this particular one is as you do all the angles on the lower half of the circle, all the r's are negative. And so guess what it does? It just traces out the same circle again. Now, of course, that's just this example, right? There'll be plenty of times where when you go on the negative, in the negative values, you're going to get all sorts of different pictures. But in this one, it just traces the same circle twice. All right, so let's confirm this, what we've done here using technology. So opening up my calculator, first of all, we've got to get ourselves in the proper mode. So click on mode, and then just like when you switch from radian degree, you can go from instead of function, where you just have your regular y equals menu, you can go over to polar and press enter. And now what's going to happen is if you go to your y equals menu, instead of y equals, it'll say r equals. And so the thing we just graphed was 3 sine theta. Now before I hit graph, let's go to our window and see what's happening here. So notice it gives us a theta min and a theta max. So you can see theta max is 6.28, so that's 2 pi. It's got a particular theta step. I'll experiment with that in a moment. And then we have our x min and x max here, and y min and y max that you can mess with. Okay, so I'm pretty happy with what I see here. So now I'm going to go ahead and hit graph. Okay, so this is what I see. Now just remember that even though that looks like an oval, not a circle, remember that that's because the tick marks are have different spacing on the x and y axis. So this is actually a good sign. So I think that I have correctly graphed this thing. So it's a circle, and let's understand that it's a circle centered at 0, 3/2, right? That's what it is. This is, and let's make a little more space here. So this is a circle centered at 0, 3/2 with a radius of 3/2, right? That's what it's got to have based on what we're looking at here, right? We are centered right here, and looks like we go 3/2 or 1.5 out in any direction to make that circle. All right, but it did ask us to convert the equation to rectangular coordinates. So if we do that, we should be able to see this circle centered at 3/2, 0, 3/2 with a radius of 3/2. All right, well, we played this game a little bit when we were doing the video notes. What we're trying to do is we're trying to make some of these things show up, right? So what do we know? R squared is x squared plus y squared. Tangent of theta is y over x. We know that x is equal to r cosine theta and y equals r sine theta. And so I can see in this problem, I actually have the opportunity to make r squared show up and to make r sine theta show up if I multiply by r on both sides. So I get then r squared equals 3r sine theta. But now that I have r squared, I can call it x squared plus y squared. And now that I have r sine theta, I can call it y. And so then we get x squared plus y squared minus 3y equals 0. And then in order to see what the true center is, we complete the square, right? So this is, oops, get rid of that, y squared minus 3y plus half of the middle term squared. But of course, you got to do that on both sides. And so what do we get? X squared plus y minus 3/2 squared is equal to 9/4, which is exactly what we expect if we get a center of 0 3/2 and a radius of 3/2. All right, let's do a couple more. And on these two, I really encourage you to try to come up with this. With example 6, I want to make a quick adjustment though. So I want you to graph r equals 6 sine 2 theta, but I only want you to do that for 0 to pi. So let's not go all the way around the circle, just from 0 to pi for example 6. So try these two, see if you can come up with the picture. Check your work in your calculator as well, and then we'll see what we get. This one's going to get perhaps pretty nasty algebraically, so what I would suggest here is you don't need to try to make your answers for what r is look pretty. Just get the calculator version of those. All right, so let's see what's happening in example number 5 here. So we want to have theta here, we want to have r here. Well, if I want to easily be able to construct this table, then I should probably get r by itself. But I can do that if I just divide both sides by cosine plus sine. So this will be r is equal to 3 over cosine theta plus sine theta. All right, and so what we'll do here is I'm going to start plugging things in. So let's see, when theta is 0, oops, I meant that to be a 0. When theta is 0, you can say this is 3 over the cosine of 0 plus the sine of 0. But that is 3 over 1, right? So when theta is 0, r is 3. So that puts me all the way over here. Okay. So let's give pi over 12 a try, right? Why not use pi over 12? So if I put pi over 12 in here, this is what I mean by don't try to make it pretty. Just plug this whole thing into your calculator, and what it should spit out to you is 2.45. So at pi over 12, 2.45, that puts me right about there. Okay, and you'll forgive me for not writing each one out. I'm just cranking that in my calculator. So when I put pi over 6, I get 2.20. So something more like that. When I do pi over 4, I get 2.12, so not much of a change there. So it's about like that. And then pi over 3, I get 3. Excuse me, not 3, 2.20. So now I'm back out here just a little. And then 5 pi over 12, guess what? It's the same thing again. It's what I had before. It's 2.45. Now I'm kind of back out here again. And then I ran out of space, but if I did pi over 2, I'm back here at 3. So it kind of looks like this thing almost lies in a nice line. So let's connect those up. Okay, maybe that'll continue. All right, so it kind of looks like that may be what happens here. So if I go to my calculator, let's see if this is in fact the case. Go to my y equals, I'll clear this out, get 3 divided by the cosine of theta plus the sine of theta. And let's go ahead and graph that. So look at that, it looks like we are in fact getting a line. Okay, so that's good. Now, one of the things I'll show you, because there's kind of a lot of work in manually typing all of those values into the table. Obviously, I didn't show most of it, but there's a lot of work there. So one thing you can do is you can look at the table here. Now, at first, you might say, okay, this isn't very helpful because it's not giving me nice values of theta. But what you could do is you can go to table set. So you go to the second table set. And instead of this delta table means like how much do you want the table to jump each time? So instead of 1, I could say pi over 12. And then if I do that, and I go to my table, then you might have trouble recognizing them at first, but look, here's 1.57, so that's pi over 2. These are the exact same numbers that we came up with manually. So that's kind of a nice way to do that. Now, you'll notice there's an error on this one. Okay, there's an error on 2.35. Okay, what's 2.35? Well, it turns out 2.35 is 3 pi over 4, so it's right here. And then it also turns out that 7 pi over 4, both of these are undefined. Now, if you plug in the cosine of 3 pi over 4, you of course get negative root 2 over 2. But if you plug in the sine of 3 pi over 4, you get positive root 2 over 2, so that's going to give you a 0 in the denominator. Now, the thing that's interesting about this is that these are the only two that don't work. So the idea here is no matter what angle I go at, as long as it doesn't get to 3 pi over 4, even if I am looking at like this angle going way out here, eventually this angle will intersect with the line at some point. But you can see that at 3 pi over 4, it'll never intersect. So that means there is never a time where, or there's never a value of r that you'll get by going out in the direction 3 pi over 4 or 7 pi over 4 for that matter. Now, what about all these negatives? Well, remember what's happening here is that, for example, if you plug in, if you plug in pi, for example, what are you going to get? You're going to get negative 3, which puts you way back over here. So all these angles in this region just give you negative r values, which puts you back up here on this line. All right, last thing here I do want to do is just let's make sure algebraically we feel good about this being a line. So if I go back to this version and I put the r through, r cosine theta plus r sine theta equals 3, well, guess what that is? That's an x. That's a y. So we get x plus y equals 3. And so that big mess was just the simple little equation y equals negative x plus 3. So you can see why, if I go back to the previous example, why polar coordinates were nice, right? The rectangular coordinate version, much more complicated than the polar coordinate version, right? Much more complicated. But in this case, I would say the polar is way more complicated. Why write a line this way when you could just write it that way? All right, let's do one more example. So we're going to graph r equals 6 sine 2 theta without a calculator. Okay, We can check our answer afterward, but we'll try to do this manually. So we'll set up our table. Oops. Set up our table here and start plugging things in. So if I put 0, I get an R value of 0 because the sine of 0 is 0, so that's not surprising. If I do pi over 12, that's going to be 6 times the sine of 2 times pi over 12, which is going to give you 3. So here at pi over 12, I'm all the way out here at 3. And actually, now that I'm thinking about it, I think I would be wise to not let this be 3, because I'm thinking that this number is going to get bigger. So here's what we're going to do. We're going to label each circle. So each circle is not going to be 1, each one's going to be 2. So we'll label it just like this. And you can always do that anytime you'd like. So when I say that at pi over 12 it's 3, I'm going to put that actually right there. That would be my 3. All right, now if I plug in pi over 6, I'm going to not show all the detail work this time. I get 5.20. So that's going to give me, here's 5.20, a little past that. When I do pi over 4, that gives me 6 exactly. That puts me there. When I do pi over 3, it gives me 5.20 again. So now I'm back down here. And then when I go 5 pi over 12, I get 3. And then when I do pi over 2, I'm back to 0 again. So it seems like what happens is I have this, maybe we'll call it like a flower petal or something like that. Okay. All right, so let me just show you the pitfall that you can fall into if you rely on your calculator too much. Okay, so we've only gone 0 to pi over 2. And you see that I want to go from 0 to pi, okay? And so maybe then you take a peek at your calculator, and in your calculator, you go ahead and type in the formula, 6 sine of 2 theta. And so when you do that, you go to graph, and that's what you see, okay? And so you think, okay, great, I just graphed this one. So from pi over 2 to pi must be this one. So maybe I'll just sketch these top 2 and call it good. Well, let's keep going. So I'm going to continue to make my table here. So what if I go 7 pi over 12? 7 pi over 12 gives me a negative 3. Okay, so here's 7 pi over 12. Instead of going 3 this direction, I'm supposed to go 3 back this direction, so it puts me right there. When I go, let's see, 2 pi over 3, I get negative 5.20. So that means instead of going, here's 2 pi over 3 here, but instead of going 5.20 this way, I got to go back 180 degrees in the other direction this way, so it puts me there. And so you can kind of see what's happening here, right? The negatives crop up as I go from 0 to pi, pi over 2 to pi. And so things are happening back here in the 4th quadrant instead of in the 2nd quadrant. And then 5 pi over 6, that's going to be negative 5.20, so back here again. And then we have 11 pi over 12, so you can probably guess that. That's going to be negative 3. And then finally, at pi, we're back to 0 again. And so what happens here, this will throw folks off, is that if I ask you to only graph from 0 to pi, that doesn't necessarily mean that all of what you see has to occur in the quadrant of those angles, because if you get negative R values, it throws you into the quadrant 180 degrees away. Now, if you want to make absolutely sure, though, that you did this right, you can still check it in the calculator. So what you then go to here is you say, let's go back to my window, and let's realize that instead of going from 0 to 2 pi, really what I wanted was just 0 to pi. So I make my theta max just pi. And then if you graph it, notice, in fact, you do get just the right two petals of that flower. Last thing I just want to point out about the calculator is that if you ever see what you think is probably an incorrect graph, here's one thing that could be happening. Your theta step might be way too big. So if I change to a theta step of 1, you get something really goofy here. Understand that the theta step is telling you how often to basically check the value, right? Or in other words, if I was making a table, it would mean that I would be making a table with theta equals 0, theta equals 1, theta equals 2, and so on. And that's not going to give you a very accurate picture when once around the circle is just 6.28. So if you ever are getting something weird, check your theta step, and that should be, a lot smaller. Just understand that, like, if you did something like this, 0.001, and you hit graph, it's going to take it a lot longer to graph because it's putting little pixels down more and more often. Okay, so that's the thing you got to sacrifice. But the smaller your theta step, the more precise your graph is going to be.